Okay, so recording has been turned on. Okay, so let's wait 1 or 2 more minutes, right, for everyone to join, and then Rohit, you can get the ball rolling.
Cool. Just let me know if you can still see my screen now.
Yes, I can.
Perfect.
All right, Rohit, let's get started.
Okay. So good afternoon, everyone. It's a great opportunity to be here with you guys. And I will, in the span of, let's say, 45 minutes, Mubasir, 45 minutes, 1 hour, how much time do I have?
Yeah, that sounds about right. And as I said, right, every few minutes, maybe pause, see if the students have questions in the chat, right, and try to answer them. Okay, but yeah, that sounds reasonable.
Perfect. Okay, so in the span of next, let's say 45 to 45 minutes to 1 hour, I'll be discussing some of the research ideas which I worked during my PhD, and followed by whatever I'm currently working on. So with that, let's begin. So yeah, a little bit about me. I'm Rohit Kumar Dubey. I did my PhD from ETH Zurich in 2020, not exactly last year, under the supervision of some intelligent people here. As mentioned here, Mubasir Kapadia was one of my co-supervisors. And after finishing my PhD, I started as a postdoc in the Technical University of Munich in the chair of computation, modeling, and simulation. So as Mupasi said, please feel free to ask questions whenever you want. It might be slightly difficult for me to monitor the chat because it generally doesn't show up. So please feel free to switch on your mic and just ask me a question. Okay, so with that basics, let's get started. So my research focus lies at the intersection of human wayfinding, architectural design, and artificial intelligence. And the goal is to how can we develop building design keeping human in mind. So basically developing solutions for human aware building design. So my goal is first to investigate the human wayfinding process and formulate the computational model of human wayfinding. So in this, I generally study the interaction of various factors present in the world as in the environment, which guides our decision. We will speak about the factors which influences the wayfinding in the consecutive slides. Then once we have the fundamental knowledge or the cognitive theory behind how the interaction of human being with the environment happens, we tend to develop a computational model of it. And then we use that computational model in some computer-aided design tool, which can empower designers and architects to design the building better with some optimization in mind. Finally, it's also important to employ some AI methods, specifically reinforcement learning as a tool, so that which can we create some heuristic, human level heuristic using the reinforcement learning agents. So one crazy idea here can be that we have heard of architectural tool which has human in loop for design process. So can we have replaced that human in loop with a reinforcement learning agent in loop? So that's one idea. So moving on, this slide generally tries to motivate the entire work. So the goal is, there are a lot of challenges which architects and designers faces to design the building. One example which you can see here is like there are multiple objective of a building. Some people are there for shopping, some are just taking a train to somewhere, someone is exiting the building, someone is there to socialize. So there are multiple functionality of a building, and keeping all of them in mind and still be able to create a very functional and ideal building is a very challenging task. So can we make this process easier? So this is the motivation behind the entire research. So let's move on to the things which generally exist in the current research. So there are a lot of building information and modeling tool as shown here, which can provide some static representation of human behavior. Also, there are some mature techniques that can simulate the aspect of buildings such as energy, its structure, what is the lighting conditions, and the wind simulation. But there are very little which actually seeks to model the relationship of the building with its inhabitant. So the whole idea is, can we put human at the center and then design the building? So, and this then brings me to the topic of human wayfinding, which was the focus of my PhD. So yeah, so basically, wayfinding is a task that we conduct every day while going to work, visiting friends, or if you, I mean, you might not be in the classroom, you were all in probably at your home, but let's say if you wanted to come to a classroom, you must have performed some kind of wayfinding behavior to reach the class. So basic activities such as shopping, commuting, and socializing requires us to navigate from one place to another. So with the rapid increase in population and urbanization, the existing infrastructure, which was probably made like 10 years or 20 years ago, or even older, are often were not designed for so many people. So it is at a stress point. So there are some statistics which says that in a sporting venue or an entertainment venues, there are like 70,000 fans. New York train station and the Grand Central Station received 200,000 passengers daily. So it is at a stress point. So can we and moreover, the current generation of designers and architects, they are very ambitious and they want to create designs which you see in the, if you can still see my mouse. I'm not sure if you can see my mouse. Yeah, let's say these designs. So these designs are very not very symmetrical, like rectangular and boxes. They're more rounded and curvy, and it's kind of difficult to remember these places. Though they look very nice, but it's difficult to navigate. So there are many factors which needs our attention. So yeah, so that's one of the few of the challenges which we are dealing with. So again, that brings back to the question, how can we design the building better? So I'll pause here for a while and ask if you guys have any questions so far. Feel free to open your mic and then just ask.
Yeah, one question. So when we say we are going to design the building, so what goal are we keeping in mind? Is it the exit or finding, or yeah? So what kind of human interactions are we thinking about?
Yeah, that's a good question. Yeah, again, there is not one interaction. So it depends on objective of the building. So let's take a very prominent example, which is like egress, like evacuation scenario. So how can we put the exits of the building, keeping the corridors and these. So there are many factors here, like the size of the corridor, how big the door should be. So let's take a very simple example. Does having one big large door, let's say 10-meter wide, is better than having two doors 5-meter wide? So how can we do that? So if you can create some kind of simulation to simulate the, let's say, a lot of crowd like agents evacuating the building, maybe having two different space will give you the objective which you want to achieve. Did I answer your question?
Yes, yes.
Okay. Any other question? Cool. So let's move on. So yeah, keeping this in mind, I will try to very briefly explain what wayfinding is. I started talking about wayfinding without explaining it. So let's go back. So we often, many people, maybe not, but some people often use the word wayfinding, navigation, locomotion interchangeably. They try to convey the same point, like going from one place to another, but they are these three words like wayfinding, navigation, and locomotion are different. So The easier way to understand is navigation is equal to wayfinding plus locomotion. So navigation is the superset, and wayfinding is the process that requires, it's like a requirement to know where to go and how to get there. That's wayfinding. And locomotion is simply the kinetic movement of a body or a UAV that brings you there. So this is the definition. Navigation is equal to wayfinding plus locomotion. So let's keep that in mind. So yeah, so a simple example is shown here. So wayfinding involves like selecting and moving along a route to a destination. So example, a person is looking at a sign, infers the direction which it is trying to figure out, and then the internal processing and interpretation of the information happens, and the action, which is the locomotion part of the navigation, kicks in, and then you try to navigate to that place. So this is a very simplistic definition of human wayfinding. Okay, so as we said, there are multiple factors which influences the wayfinding, and those factors are broadly divided in these big categories. So one of them, there are two major factors. One is the external and the other one is internal. So the internal factor is called knowledge in the head, which is what you have built up based on your experience and growing up and visiting the environments. And the other one is knowledge in the world. So knowledge in the world can be, one of the example is signage. These are in directional information in the world. There are landmarks, there are different crowds, there are different spatial layouts. I will go in each of the factors in detail in consecutive slides, but for time being, just believe me that these are the factors which impacts your decision making while navigation. There are other physiological factors like eyesight, height, and psychological factors such as perception, interpretation, stress level. Like evacuation is a prime example when you are highly stressed, and there are chances of you making mistake. Even if you see the sign, you're not able to comprehend it because of stress. And then again, culture, background. For example, I grew up in India, so we walk on the left-hand side, and some people in the Europe or the America, they walk on the right-hand side. So these are the cultural aspect. Gender also plays a role, but let's not go too much in detail. So in general, these are the factors which impacts the wayfinding. So let me pause here. Do you have do you think, did I miss any other factors? Or do you think it broadly summarizes everything?
So Rohit, maybe one question related to what you just said. So how did you, as a scientist, come up with this taxonomy or these set of factors?
Okay, so it was a long process, basically going through the literature in the field of spatial cognitive science, discussing it with a bunch of lot of architects and colleagues, so industrial partners as well, and your own intuition. So basically, when I went to a shopping mall, and then I was very conscious about my decision, that why am I taking a left? So it was both either in the environment which I'm familiar. So how do I use my memory? Because I've already been in the environment, so I have some rough idea. And sometimes in an unfamiliar environment, where how exactly did I do it? So one prime example which came in, and why I included crowd here, was that sometimes when I exit a train, like a MRT or a train, I do not know which direction, left to right, the exit is. So wherever I see a lot of crowd going towards the staircase, I just follow them. So crowd influenced my behavior of following people. So these were the basic way of how I came to this taxonomy. Okay, so let's move on. Okay, so this is a very simple video, which I wanted to just highlight here, because this is a simulated video of an agent. Let me play it. I hope it plays. Yeah, of an agent moving in a simulated environment. So this is a realistic, this is a shopping mall, a real environment in Singapore. And this is the 3D model of that. So what we see here is Like an agent is walking and observing different aspect of the environment, and they are influencing the decision making or just navigation process. And things which were highlighted in red were the objects and artifacts which were observed. So let's quickly move on. Yeah. So okay, so this brings back to the question which Mubasir asked, that how did I elected everything, and basically all the factors, and what was the entire approach for building up this research. So so this architecture, this diagram framework, it tries to explain it, and I'll try my best to try to explain this. So what we do is, first, as stated earlier, we identify the factors. So if you see these, number one, it says experimentally driven cognitive model. So these are the factors I elected to study: signage, space, memory, crowd, and history. Not so much, but let's ignore this for this talk. If anyone is interested, we can discuss this. But let's assume that there are four factors: signage, space, memory, and crowd. So first we elect these variables. Now, once we have variable, now we need to know how do they individually or together interact with human beings. So how does signage impact me, my decision making, or with a human? So then what the most how should I say, the ideal method or the scientific approach towards it is that you conduct an experiment. So you can conduct an experiment in multiple ways. The most prominent way is you can do it in real world, but it comes with its own challenges. So one challenge is that you cannot control it. So let's say if I am conducting an experiment in a real world setting or in a Grand Central Station in New York, I do not have a control of how many people will be there, which person will walk in what direction. So this can cause a lot of noise in data collection. So conducting a real world study is very important, but it needs to be controlled. So there are some challenges. So to avoid that, or to overcome it, we try to do that in VR. And there are VR as in virtual reality. And there are multiple ways of doing the experiment in VR. So the easiest one is the desktop VR, that you have a computer screen. If you can see the guy sitting or the person sitting in front of a computer screen, you give them a task which is shown on the monitor, and the computer and the person performs a particular task designed by an experimentator. The slightly more immersive way of doing the same experiment is using the headset. So like HMD head mounted devices, which you can is very prominent now. So it improves a bit of immersiveness, but it has its own challenges of nausea and everything else. But so far, head mounted device have rewarded all my experiment pretty well. So that, and let's say if you want to collect a lot of data, like in thousands. So conducting a desktop-based VR experiment or immersive VR will be very time consuming. Like you have to bring each participant in a lab, then they have to go through the entire process of learning, and then 1 hour of experiments, and it can also be expensive. So the other way is to do a crowdsourcing. So there are multiple ways of doing crowdsourcing. One is like Amazon has MTurk. I hope everyone is familiar with that. So it's a place where you can, it's like hiring Turks. So those are the called, that's why they are called Turks. So there are people, the real people in the world, they can just participate in your experiment based on the initial condition which you have set for them. Like they should not be of below 18 years or above 70 years or something like that. And the other way of crowdsourcing is that you can develop some apps. So if you have a mobile phone and you can generate an app, so current game engine, not most, I do not have an example, but they generally, the games which are running on your mobile phone, sometimes they collect your pattern, your behavior in the game, and that also helps them to make some kind of understanding. So yeah, so that's is how we conduct an experiment. So now we have a variable. Now we know that how to conduct an experiment. So now we design an experiment. That is also a very important part. So experiment can be as intricate and complicated as possible. But for example, let's say I want to understand how a human being interact with a sign. So what I will do is that in a virtual reality experiment, I will show them a simulated model of a sign in a real world setting, which is of course a 3D model of it, and will give a task of a person to try to find a particular destination, and then the person will go through the environment, probably see a sign and perform the decision. So this is a very simplistic example. You have to control many other things, but let's go with this example. So this is how you conduct a simple experiment. So now once you have conducted the experiment, you collect data, the whole point of the experiment. And the data can be multiple. Is the trajectory of the person walking in the 3D environment. So you have a trajectory. You also know where that person took a turn at an intersection. If you are performing eye tracking, then you can know if when the person exactly saw the sign, how long the person kept looking at the sign. So you can have those eye movement data as well. So these are your data. Now, once you have a data, you can run a statistical model, depending on what kind of experiment you do, to infer what is the understanding. So in a simplest term, let's say if you come up with I don't know, a formula like A equals to B times C, and A is what you want to know, and C you already know from the data. So you can compute B. So this is how we frame the experiment in the form of an equation. We will discuss one particular example in the coming slides. So now once you have those, let's say a computational model of how do you see a sign or anything, then you use that and give it to your agent. By agent, I mean a 3D avatar, because we are running simulations for crowd movement and cognitive model. So we will give that computational model to an agent, and the agent behavior is guided by that. So instead of having a static or a fixed movement like A star path planning, which will always be similar, now you have a computational model which is kind of dynamic because it depends on the environment in which the agent is getting simulated. So it brings you closer to realism, more human-like. So I will pause here again. Maybe someone has some question about it.
I have a question. In the previous video that you showed that we have a shopping mall and the agent was moving around. So do we assume any goal state here? Because there can be scenarios where we don't have a specific goal and we are just running that one. So all these models, or let's say the wayfinding, so do we always have a goal state in mind, or do you also incorporate that we're just freely roaming around? Behavior?
Yeah, so if I understood you correctly, so for conducting an experiment, we always have a goal state in mind. So there is always a task given to the participants. But there can be some task where there is no goal. So sometimes when we want to, let's say we want to come up with a model which performs a random exploration pattern. So for many video games, you have non-playing characters like NPCs. They are mostly there to randomly fill the environment or crowd it, and then they do some kind of navigation. So if you want to do those random behavior, you can let the participant randomly explore the environment. But again, that no participant randomly explores the environment, because the at the least environment has some spatial attributes to it. So it will pull you towards a particular corridor. So it depends on the textures, on the space. We will discuss all those things. So in short, when we conduct an experiment, there is always a goal in mind. And there can be a goal which is no goal, like random exploration. Okay, cool. So this is the entire approach of taking. So yeah, so we were discussing individual variables. Now in future, like once you have studied the interaction of how signage behaves or influences your decision, you can have conduct similar experiment with space, with memory and crowd, and understand them individually. But again, the real world does not have individual information. It has combination of these informations, and sometimes you can only see signs, sometimes you are familiar with the place, so you don't even want to see the sign, you can just go. So then you can conduct experiment by combining them together. So that again becomes a long process, that how many combinations will you combine? Like there are 4 variables, then you have to run 16 experiments, something like that. So is there another way? So there are a lot of ways of multivariate decision making, that you can combine all the variables individually and then compute their uncertainties and then come up with a common decision. So which is like, let's assume that this is how we do it. Okay, so now we have discussed all the approach. So now I will go through 3 or 4 experiments which we conducted, which is like 3 or 4 research papers, and talk about them briefly. So we spoke a lot about signage. So this is one of the publication which I had with Mubasir, and this is to discuss how do human interact with signage. So as discussed, signage is like a very critical spatial piece of information, and a proper signage can improve our wayfinding performance and also user experience. Like once you're in an environment, if you don't see any directional information, you're not very comfortable in it. You always have a slight stress that am I lost? Am I going in the right place? So signage is a very important aspect. So yeah, and so I won't go into the details of how we conducted an experiment about this, but this is the result. So if you can, I'm not sure if the sign is visible because it's the actual size. So at this top location where my mouse is on the right top part, you see a sign. And this entire area which you see as a heat map is we call it a visual catchment area. So this visual catchment area is an area in which once you are inside this area, let's say you're walking and then you come inside this area, you can view the sign and also you can perceive the sign. So this heat map explains how much can you, so what is the probability of you seeing the sign, and on top of that, what is the probability of you perceiving the sign? So there are 2 different things. You can see the sign, but sometimes when you are walking in an environment, maybe with your mobile phone or daydreaming, or because of some other factors, you may not perceive it. You just saw it, but you'd never bothered to comprehend it. So we conducted these experiments and figured out, and that's why these heat map, what you see is, so the grid cells which you see with the warmer color, that is the red, represents the high entropy and the uncertainty. So basically, once you are at the edge of these visual catchment area, the probability of you perceiving the sign is very low, or you have a lot of uncertainty. And to improve upon, you gradually go closer to the sign. So you can see that once you start reaching closer to the sign, the grid cell becomes cooler in colors, like as shown here in green. So there are less uncertainty and you're more confident about perceiving the sign. So this is the model we computed after conducting an experiment. So once we have that, now we have to provide this factor, this particular model, to our agent. So this is a brief, the entire, let's say a state machine, which is like the interactive process of how we see the sign. So it consists of a series of phases, which includes like you first look for sign, then you detect a sign, then you try to approach a sign, then you do information, you try to gain information from the sign. And once you do that, you make a particular decision. So you act on it. So the key idea is the information gain phase. So this particular research was focused on computing the information gain phase, which means, so before coming here, the previous work had a very binary version of it. So if I can go back to the previous slide. So in the previous work, what existed was, so if you are within this, let's call it a rough circle. If you're within this circle, you can see the sign, and if you're outside the circle, you cannot see the sign. So the previous research had it in a binary form, but what we did is that we extended the previous work and made it continuous. So it's not always the case that once you're inside the sign, it's always 100% accuracy. There are still some chances of you not seeing it properly or comprehending it. And that is what this information gain phase means. And this also is very important because let's say if we go with the previous method, again, go back to the images. Someone is walking, and at this corner they can see the sign and they can immediately turn left or right based on the information. But and if you simulate that many times, let's say simulate a crowd, it might not give the right location of bottleneck, because some people might go all the way close to the sign and then take a left. Some people, so the whole point is that making a decision at the edge of the VCA or somewhere closer to or inside the VCA is not always correct. So the more realistic way is that it goes much closer to it. So you try to approach a sign and then make a turn. So this decision point can help you simulate or identify bottleneck in the environment in a better way. And moreover, if there are occlusions, let's say pillars or other people in that, this particular model can also accommodate that. So yeah, so this is, I will pause here. Maybe someone has some question here. Okay, let's move on. So yeah, so this is an example which has some relationship with the current previous work which I showed, but in general, what we notice here is that there is two different character. One has cognition on the right hand side, and one doesn't have cognition. So there are multiple signs. Both of them are viewing the sign. So one agent on the right look at the sign and takes a left turn, because taking a left in the signage, it was written that it is faster. So when you are at an airport, you see that one particular gate, they write the number of minutes which will take for you to reach it. So the agent which views the sign properly with, so we call it with cognition, may end up reaching the goal faster and probably in a more realistic way compared to the agent which doesn't have the cognition. So this agent on the right hand side already reached, and the left hand side is took a detour and went in a different, I mean, there are multiple ways of reaching the goal, so it took a slightly longer. So the whole essence is to bring this cognition and try to create a realistic walking behavior rather than always the shortest path or the or I don't know, or the one which has least number of turn or something like that. So yeah, so that's the result. No, okay, so that was about how do we compute the influence of a signage on our decision making. Do we have any question for that particular project? If not, I'll move on to the case study and the application of that. Okay, so now another form of doing the research is, I'm not saying that I completely did that form of research, but one way is that there are two forms of research. One you do a fundamental research, that you identify the underlying mechanism of human behavior, and then once you know that, you can apply that in a real world setting and create application out of it. So this particular example which you see here, the adaptive signage system, is a work with a colleague of mine, Dr. Zhao, and we created something called adaptive signage system. So let me just run this video. And so what we are seeing here is a bunch of agents looking at the sign and trying to evacuate a museum. And this museum is a Cooper Hewitt Museum. And since we can't conduct it in real world, we can't put it in fire. So we did it in the VR, and the agents have to evacuate this particular museum. And So yeah, so let's come back to the goal of this. So we were trying to understand the difference between the adaptive signage system and a static signage system. So most of the current evacuation signs are non-adaptive, like they're static, they never change. Even if a particular route or a path is blocked due to that particular area or a hallway or a corridor being on fire, people will still don't know, they will follow the sign. So it doesn't give you that, okay, don't take that road. So this is the static way. And then there is adaptive signage system that facilitates wayfinding, which during evacuation by we can optimize the route. So once we identify which part of the environment is on fire, we can change this dynamic signage to either put a green tick, which means that you can take this path, or a big cross like no, you do not enter this particular corridor. So what we found is, so this what we see here is the trajectory created by all the agents. So this is like the data which we collect once we run it. So this was one aspect of the sign. So I will show the result in a meanwhile, but the other part was that the signage was also centralized and decentralized. So centralized system means that there is one server which is giving the directional information to these dynamic signs, but at one center location. And decentralized means that every sign decides on its own. So there is a drawback in both the cases, like pros and cons for both. So centralized is like, let's say if a centralized server gets damaged in the fire, then all the signage system will fail. But this is a faster way that one server is controlling all the nodes. And then in the decentralized system is like all the sign has to compute all the information. So it's kind of costly. But it has redundancy attached. So it is more resilient. So even if one particular dynamic or adaptive sign is on fire and gets damaged, all the other signs will still be working. So so let's quickly go through the results. So what we see here in the results, so this again, we to prove what we did makes sense, we conducted an experiment both with real participant and with simulated agent. So what we saw in the earlier video was simulated agent, but we also did it with human participants. So what you see here is like this is the adaptive sign. So this is this SSSQ score is like a short stress state questionnaire. So it identifies how much stress a particular human participant is. So once they perform the experiment, we give them a questionnaire and they fill it. Based on that, what we notice is that in the adaptive signage scenario, the distress level is quite low compared to the non-adaptive, so which is a good thing. So this is in one way showcase that having an adaptive signage system performs better. Again, you can also see on the right hand side the path length, like how long does it took for overall participants to evacuate. So on an average, what you see is that if you have adaptive signage, people tend to have to take less number, so they walk less to exit the museum, so which is also good, and this is directly proportional to the time and the damage to their health. So doing this, we can statistically prove that having an adaptive signage system is better than non-adaptive system. I agree, it's very intuitive that yes, having an adaptive system is supposed to be better, but in science we need to prove these things. So you have to conduct an experiment and prove it. So you have a hypothesis and then you either prove the hypothesis or disprove it. So yeah, that was about the adaptive signage system. Do we have any question on that? Cool. Let's move on. So this is another case study for the same signage. So now we know how, so we are trying to exploit everything what we did with the understanding of the interaction of signage and human behavior. So in this case, we call it AutoSign. This is a design tool, and AutoSign as in it can automatically design the signage system of an environment. So the whole goal is that you're given an input system, input layout. So what you see here is an input layout. We do some processing and then we conduct. So I'll come to the main part in some time. So I'll just lay out the foundation here. So it can place the signage just by the input, the two inputs. One is the layout, the floor plan, and then the exit and the entrance point of that building. So once you give this as an input, this tool can give you the location of the signage with the text on the sign that, okay, so this sign should be placed here, uh, and yeah, so these many numbers of signs. So there are many benefits of it. First of all, it helps you to automatically design the signage system, which is not a trivial task. If you ask the designers, it takes a lot of time and it's an expensive process. So there are a lot of company which charges a lot of money to do this. So there is a small video. Mubassir, if I switch on the audio, will it be clearer for everyone? If the video audio?
You can try.
Can you hear the audio or is just me?
No, I think you need to redirect the audio to the mic. So
okay, so never mind. I'll just quickly explain it. So let me pause this. Okay, so what you see here is so first we have to compute the decision, like the intersections in the building, right? So these are the nodes which identifies the decision points, where if you reach to these points, if you can take a left or a right or something like that. So in this, you have 3 sub nodes. At this point, you can either go in the left, right, or whatever. So once we have these terminal and start node, you can create these navigational graphs. So what you see here is the navigational graph for the entire floor plan, and the heat map defines which node is most visited. So once you do that, you can save the path and all those things, and then this signage system gets designed. So it says like, okay, so you can, it has a very basic UI, so it's not like a commercial tool, is just an open source tool. So now the user in loop. So a designer who is using the tool can play with the sign, like move in what you saw here, like can take the sign and start orienting it properly using the mouse. So you can start designing the exact location. So there are many factors which we compute to optimize it. I just quickly want to go to the result, which is, yes. So if you see here, what we notice is the distance. So if in the non-optimized signage system for a particular task, it was let me pause there. It took a longer time to go from A to B. Just assume that A and B are the start and the end point. And in the optimized scenario, it was the distance traveled was less. So placing the sign at the right place is fruitful. So the designers aim for that. Similarly, so what I want to, yeah, so let's check this this particular result. So what we see here is in the pre-optimized stage, that is, we haven't optimized the location of the sign. These are the heat maps. So heat map says this visualization showcase what is the stay duration. So if an expert was trying to navigate, the expert was kind of confused, like either go left or right, because maybe the signage was pointing in both directions. Some of them are longer path, but even though it will reach, but it's a longer path. So it also causes some kind of inhibition. Shall I take a left one or a right one, or the right direction? And once we optimize it, we get rid of those unnecessary longer path and then the shorter path. So what we see here is that the stay duration becomes slightly lower. So this is also improves the building performance in terms of general circulation. So let's, okay, so this is another example. So initially the sign was, so our tool is not perfect, right? So we designed the sign, so and it was placed here, which was hiding behind the wall. This is the sign, and this green heat map, what you see is the visibility zone. So if you're walking from down here, you will not be able to see the sign till you reach this zone. So we had a second pre-processing stage, like post-processing stage, where we optimized this location of the sign. So this sign was slightly moved and turned. So now the visibility zone increased by a lot. So this is how we can also improve the visibility of a sign. And if we do that for all the entire signage system, we will see these results, that what you see is that it starts covering a bigger area. So more or less, there was an 18% increase in the signage coverage area. And you remember the earlier circle which we discussed, the same model was used here as well. So yeah, so basically this is what this tool does. So is there any question for this? Okay, so next slide. Okay, so now we saw how signage interacts with our decision making. Then in one of the variable which I studied was how space influences your decision making. So this particular research which we did was to first identify the impact of spatial layout on road decision. So so to describe this, I will have to explain ISO-West. Do you guys know what ISO-West is?
Let's assume no, and you can give a high-level introduction.
Okay, so basically we need to quantify space. It's difficult to quantify space, right? So space can be 2D and 3D. So let's go with an easy example of 2D. So ISO-West is a mathematical way of quantifying the space. So ISO-West is, can I zoom in? Okay, so if you can see this, my mouse and this particular corridor and intersection, what you see here is that once you stand at this particular location, there is a zone like your vision cone, which is the amount of area or sorry, amount of space which you see. And that vision cone is some kind of a polygon. And that polygon is defined when it hits the boundary. So it's like a ray casting. So you're standing at a location, you have an eye, and there are a bunch of rays, which is actually how we see the environment, gets reflected back from the environment to your eye, right? So you have a space around you, which you can see. And that is called partial ISO-West, because we are talking about how much can you see. There is a complete ISO-West is like 360-degree around you. So even you can see behind you. So let's assume with the partial ISO-West, like it's a field, it's a vision cone. So ISO-West is that polygon, and every polygon have multiple features. So there are like 17 features, but the prominent ones, which is like it has an area. So a polygon, you can compute an area. It has a perimeter. It has the drift and the occlusivity. We'll see what are those. So ISO-West is a way to quantify space, and it has a bunch of measures: area, perimeter, occlusivity, and all those things. So this is how. So now we have a tool or let's say a formula to compute to quantify space. So we have that. So now what we do is the goal of this particular project is how can we first to understand the relationship between the space and a human, specifically at an intersection, so at a decision point. So once you are at a decision point, let's ignore there is no sign. I mean, just assume that there is no sign in the world. You have never been to the environment, and all is there which exists is space around you, and you want to make a decision. Should I take a left? Should I take a right? Or should I go forward? So let's say if the space is a dead end, you know that there is nothing else. So the space is telling you that it's a dead end. So you turn behind and you take a U-turn and you start walking back. That's one very explicit example. The other examples are, let's say if I want to go to a washroom in a shopping mall, you know that washroom are not at the center or near the atria of the building. It has to be at a corner which is not like the main corridor. So it is like a minor circulation path in a building. So you have these intuitions. So these are intuitions you gather from the space. So one example, so we have that space. Now the space which is which is wider in corridor. So let's say if there is a Y-shaped junction and you see one corridor which is wider and one corridor which is narrower, there are high chances that you will end up taking a wider corridor. This is just this has been demonstrated by conducting experiments. So you get pulled towards a space which is wider. So so far so good. Is there any doubt till now? Okay, so I'm assuming everyone knows, has understood so far. Okay, so now we have these. So these are the general understanding. So we conduct an experiment now to actually quantify which parameter of the iService, or sorry, which measures of the iService impacts your decision. Not everything is statistically significant. Like you need to know if area influences more than perimeter, or it is the occlusivity or something like that. So we conducted an experiment again. So do I have a field? Yeah. So let's discuss this one. So before conducting an experiment, we have to identify the environment in which we need to conduct the experiment. So what you see here is the floor plan of real world building. So this is the 3D model of the real world building, all the important, not all, but some of the important buildings, and all different shapes and sizes. So you will see a lot of irregular shapes, circular shape, and some one looks like a starfish. So let's take that example. So what we did is that we computed this iService feature. So if you can see these points, so these are the features of iService. So of one particular example, let's say 12. These are the 17 features which you extract, and some of them are area, some of them are perimeter, and so forth. So we have these iService features, and then from there, what we do is so we have discussed this. Let's go here. So in this case, we have a 360-degree view shed, which is the iService, and we extract 500 different intersections from this set of 17 to 18 floor plans. So every floor plan will have 10, 15 intersections, right? So out of that, from 17, we could manage to get 500 intersections. So now this is our data point, 500. So in that 500, and there are three. We divided iService into 3 sets. One set includes all the measures, let's say all 17. Then there were 2 sets, which was one proposed by Benedict. Benedict was the person who invented iService. So we should definitely use the one which that author highlighted, that they influences your decision making. And the third one is we handpicked it from the literature. So people do conduct multiple experiments, and someone says that area has an influence. Some other paper says perimeter has an influence. So we picked all the important ones and created a set 3. So now we have 3 different sets. And then we performed the clustering process using k-mean with all the 3 different sets. So what we see here, the green line, you see is it has the highest objective functions, and it gives you number 5. So it gives, and when you also try to count on the right hand side, you will see that there are 5 distinct and unique clusters. So we then from 500 intersections, we computed, we can divide them into 5 clusters. So this whole process of clustering was to separate the data in unique clusters, because we can't conduct an experiment in 500 intersection. It will take like multiple days for one person to go through all the experiments. So then we divided into clusters. Then out of 5 clusters, we picked 10 from each. So now we have only 15 intersection. But the whole idea is to have these 50 intersection, which has an equal contribution of all different kinds of intersections, so that data collection, I mean, many of you know that the data is very important for training any machine learning algorithm. So this is crucial to have a right set of data so that we can get right set of understanding. So doing that, we conducted an experiment. So the experiment looks like this. A person is approaching a particular hallway corridor, which you see here, and a decision point. and the person observes. So this was conducted in the head mounted device. So we can compute the isovis from there. And the person can see 3 different isovis. One is to go on the left hand side, go straight, or then the right hand side. And we compute this, and we also, along with their isovis, what are they seeing, we also compute what decision they took. So once we have both the data, we can come up with a statistical measure. So for time being, you can ignore all these things. What it actually does is, so for people who knows a bit of statistics, this was a conditional logic model. In this, we have parameters like there is an area, then there is O for occlusivity. Okay, one thing which I forgot to mention was that we found out that the area parameter, so this was set to perform the best. This is what we found out. So now we have these 1, 2, 3, 4, 5, 6 measures. So I think 5 of them performed best. I'm forgetting which one, but yeah, one was almost the same, not statistically significant. So anyway, so coming back to this equation, so we have an area, occlusivity, skewness, and jaggedness. I think G stands for jaggedness. Yeah, J. So this is a formula where we have a data of the decision making and the probability of taking which particular intersection route or corridor they chose. So what this says is, like, let's say Pi. So I is the intersection number. So you are at one particular intersection. J is the probability. Yes, so J is the path which participant took, and K is the direction from which the participant came. So if you see in the figure, if you're coming from this direction, you have 2 options: go straight or right. So K is this direction, and J is the one which the participant took. So you can compute the probability for each. So like coming from any particular direction and going in any particular direction, and this we can compute using the data we collected. So this gives you the probability. So once we have the probability based on the experiment we computed, we have so this is something which we can use now to optimize. By optimize, what I mean is that you have a ground truth. A designer wants a particular circulation way in a flow plan. So a simple example is an airport. So you must have noticed, or in future, please notice that when you are trying to go through your gate, immediately after an immigration, you will see a duty free. They force you indirectly to go through duty free. You can take another example, but more or less everyone has to go through duty free. So these are the ground truth. A designer wants each and every traveler to go through duty free because some people might buy towards it. So let's imagine that we have that kind of a scenario, that I want all my let's say an occupant in a building to go through the central atria of a building. So that will, now I know that I have to design a space so that I can push people or pull people towards the center. So this is your ground truth, and now you know how can you at an intersection which isovis gives you what kind of probability, what probability of taking which route. So now you can start optimizing the space. So I think if I show, I'll come back to the results, but let me quickly show you this video. So what you see here is the environment is getting manipulated at the intersection mostly. So this is very short. So basically this is what we do. So we try to manipulate the intersections so that the corridor which we want people to take most starts shaping up. So by changing the environment, the geometrical structure of the environment, you actually are changing the isovis measures. And we now, from the previous example, we understood the influence of isovis on your human behavior. So we are trying to implicitly nudge a particular decision-making mechanism for a particular flow plan. So this is what we did in this paper. So coming back to this result, we can quickly see the results, like the one which says our approach 2 has what we see are highlighted here are the area. So the initial baseline was this on the left hand side, and after our method and we optimize it, we can see the new heat map, and all the areas which are marked in highlighted in warmer color like red and circulated means that the area of, so we are only showing the result for area, the measured area for the isovest, it increased, and we know that higher area has more influence on the decision making. So we could totally notice that after optimizing, we could improve the baseline from the baseline. And gold standard is like an architect takes the baseline and tries to design the flow plan according to the wayfinding circulation as per designer's choice. So yeah, this is what this particular project did. And in terms of quantifying it, we can see that when we run the objective cost function, we achieve a slightly lower, better results compared to both baseline and gold standard. So yeah, do we have any question for this part? I know I went through very quickly, and there are so many things which I skipped. Okay, so Mubasir, do I have another 10-15 minutes to go through it, or should I just explain, go with one more and then wrap it up?
Yeah, I think in the interest of time, maybe another 15 minutes to conclude your talk, if that's okay.
Okay, so let's, if I do both, it will take more. So let me just come to this important one. So the part which I skipped was how do we, so yeah, very quickly. So this part which I'll very briefly go through is identifying the landmark in the environment. So what is a landmark? So have you noticed that when you ask a direction in the real world, someone will tell you like, do you see the yellow post office or a red color building? Take a left from there. So this red color building is a landmark. So not saying that only buildings are landmark, just giving an example which highlights very clearly that what landmark is. So landmark is any object in an environment that is visibly distinct from the object, at least in its local neighborhood. And that also helps you remember the place. So you will remember the place, like let's say if you have been to Paris, you will know where Eiffel Tower is, and you can use Eiffel Tower to give any direction. You see Eiffel Tower, it's towards the east of it. So Eiffel Tower becomes the landmark. So yeah, but we never saw a lot of work which automatically identifies a landmark given a scene. So you can identify it in the real world and also for an indoor environment. So this particular work is computing automatically identifying the landmark in a 3D environment, so which is in the indoor world. So in the question answer session, we can come back to this if you want to know how we did it. But for the brevity of time, we will just move on. The reason why I discussed that briefly was because I want to discuss about this cognitive path planning model, which involves spatial memory distortion. And to discuss this, I wanted to explain what landmark is. So now we know what landmark is, and we should also understand that when we are, so this is about memory, spatial memory. So when you are in an environment, you develop a mental representation. So for example, if I ask you to close your eyes and try to draw a figure from your current place to, let's say, your favorite cafe, you will be able to make a graph. Like you will start with a node here, then connect an edge, and then you can plot it. So that is what I meant by the spatial representation of the space. That is your spatial memory. It can be short term and long term. So let's not go there. Let's assume just that there is a spatial memory if you are in a familiar environment. So this particular work is basically to increase the immersiveness or a realistic path planning model. So there are multiple AI-based path planning model, like there is A star, there is D star, and there are many more, which are more or less gives you the same static path all the time. But human beings do not walk like that. We first of all, we very rarely we take the shortest path unless you completely know the environment. So there are high chances that you might not end up taking the shortest path. So in that case, how can we simulate that error in a human path planning? So this entire part, the framework is to add in the error. It's not to create an 100% accurate model. It is to include all kinds of errors and distortions and noise in our path planning model. So to come up with that formula, we need to create the graph which I was speaking about. So there is something called cognitive map. Cognitive map is, let's assume that this is a navigational graph inside your brain. It's like inside your memory. How it happens, it's very intricate. So let's just assume that it is a graph, and this graph is being proved that it is an hierarchical in nature. And by hierarchy, so if you see this figure on the bottom right, this is the this is the hierarchy nature. So after conducting an experiment, we identified that there are three different levels to this cognitive graph. So we call it dynamic hierarchical cognitive graph. Now there are two aspects of it. Okay, so one very quick question. I'm not sure if I used an example from USA, but let's see if you guys know this. If I ask you, can you point where is, so let's say you are in San Diego. San Diego is in California, and I want you to give me a direction which points towards Reno. Reno is a place in Nevada. If you guys don't know, then this experiment doesn't make sense, but just make a guess that you are in California, San Diego, and I want you to give me a direction like north, northwest, or southeast, or southwest, in that which points towards Reno, and Reno is in Nevada. Can you give me a direction?
Yeah, folks, if you can put your answers in the chat, that would be great.
Okay, let me.
So yeah, a lot of northeast, some east.
Yeah. Yeah, so good. I wanted to bring out this particular aspect. So thank you for giving me the answer which I was looking for. Yeah. So why did you do that? Because there was some kind of distortion in your memory, basically because of the figure I showed you. I purposely told you that it is in Nevada and in California. So let's see. Okay, let me get rid of this. Oh, come on. Anyway, so yeah, so this is what most answer was, not this. The whole point is Reno is here and San Diego is here. So the actual direction is north-northwest. But there was some, so I don't know if you were influenced by the map which I showed, but in the absence of this map, you rely on your memory, and your memory will get distorted at a higher level of the cluster. Remember, the cognitive graph which we discussed has three different layers. So you have a category or a cluster which is California. The lower level from California are the individual pieces, let's say San Diego and all. So in your brain, you know that California, Nevada is towards the right of California. So probably Reno has to be towards the right. And that is what you got biased by that. And most of the people will take that choice. So it is point to northeast instead of north-northwest. So this particular part, the entire model which we created was to include such distortion in the path planning model. So I hope I could explain that. So this particular example is called the distortion, which I said is, I want to get rid of this. How? Yes. So what we just discussed was the category adjustment. We can come back to this figure and actually figure out how do we compute it, but I will skip it. Then there is, so that was the first kind of distortion, the category adjustment. You, based on your category and cluster are interchangeably used here. Based on your cluster, you get biased. The second one is the sequence order shift. So this distortion is basically, so what you see in here in the figure is like, let's say you are this person and you're walking the environment. So the underlying is the environment, the floor plan. You're walking from the left-hand side to the right-hand side. And there, in between while walking, you see a lot of landmarks. So these small figures highlights the landmark. And you see them while walking from left to right. So once you try to cluster if you put a tight ellipse around the landmark, the actual centroid of that ellipse will be this point, which is shown in the lighter blue color. But since you were witnessing it or observing the landmark from the left hand towards the right hand side, the center of that centroid gets shifted towards you. So towards in the order of the first landmark has the maximum impact on your memory. It should be the other way around. It's like a little non-intuitive that the last thing you see should be the most crucial one because it's fresh. But generally what happens is the first thing you see has a bigger impact when you try to start recalling. So yeah, so that's the sequence order shift. So this centroid gets shifted here. So once you are doing a path planning model, the new centroid which we need to consider is the shifted one rather than this one. And these are the noise which we want to include in our path planning. So this is basically the three different levels. So if this is the bottom layer, so these can be individual locations like let's say San Diego and all the other places. This can be the California and Nevada, and this can be now in terms of USA and Asia. So it has this category at different hierarchical level. Very quickly, and then we go to the result and I conclude, is this. So there is a lot of heuristic which people try to follow when they walk. So some people, if next time when you're walking in the environment, just observe if in an unfamiliar environment. Some people try, if you don't know, that you keep going straight till you reach an intersection and then you make a decision. But so this is one way of walking. Some people end up, so if it is a multi-floor building, some people try to first go to the floor in which they want to go and then try to find the location. Some people on the lower floor keep going towards the end and then take the lift. So there are multiple heuristic, which is very dependent, individualistic. So there is no one way. But if we can sum up or based on literature, what we know is that there is this particular heuristic, which is mentioned here, find to coast, is the most common one. So based on experiment, we have observed that this is the heuristic which many people do. So for example, what it find to coast means is that when you're doing a path planning, you pay more attention locally, and the distant part you roughly calculate it. So if you think from a computational point of view, you cannot give the equal amount of memory for all the nodes. So if you have a graph and the graph is huge, you cannot compute path for each and every case in the node. So you create some kind of hierarchical and categories so that you can just pay a lot of attention in your local neighborhood and then forget about or do a very coarse path planning for the distance one. One easy example is, let's say if you're taking a route from one state to another state, in your brain, you are only focused on how from your current house or someplace where you are to the closest highway, which brings you to the state highway. So you focus more on reaching towards the highway. And then after that, you will make a plan. So that's the course plan which you start with in your brain when you start traveling. So this is what it means. And in the example, what you see, I try to explain the same thing, is that let's say if you have start at this current start point and you have to reach the goal, the traditional method will take you towards from node 11 to 9 to 10, which is highlighted in orange. This is the path. This will be the path given by the traditional route. But find to course model, what will do is that it will do a find in this category, which you see here, but then it will do a course level path planning. So it jumps on the higher level. So it will be 11, 9, followed by 17, followed by 18. So what you see is that the computation was much lower than the so this is a small case. Imagine this graph being big. So this FTC is computationally fast as well, and also more realistic and human-like. So very quickly, I will show you the results, two results. One is from the real world and one is from the Manhattan grid. So this is the simulated world. Both of them are simulated, but one is based on real floor plan. One is artificial synthetic based on Manhattan, New York style grid structure. So what we see here is, so the trajectory mark in blue is the simulated one, and the trajectory in red is from the real participant. So we gave them the same task from going from this, let's say take this example, from the left-hand side to this point. And these were the real trajectory. And our simulated trajectory, the agent could also mimic a very similar one. So you see there is a blue line which is not visible, but it also takes this path. So we could simulate similar human-like trajectory using this method, using the noise. And below what we see is the path. If we take a simple A star, you see that the paths are very static and very symmetrical. But if you start using find to course model, that is what FTC means. And then if you add, so we discussed two distortion. So this is categorical adjustment and this is sequence effect. So once you include these things, you start seeing variation. And this is somewhat how real human walk. If you don't know it, or you roughly know it, and you have some noise and distortion, if memory is fading away, you start taking these trajectories. So this is what the result is. And there's a video, but let's skip that. Yeah, so with that, I'm done. This is my pitch for asking if anyone is interested to work with me. I have also posted this particular synopsis on the Discord channel. So please get in touch with me if you're interested in working in generating a 3D layout from the 2D floor plan. So yeah, with that, I would like to thank everyone for listening, and I'm happy to answer any questions. Thank you.
Awesome. Thanks a lot, Rohit.
Yeah.
So I think what's perhaps important to say here, right, is that essentially what Rohit just presented, right, is the culmination of research done over 7 years, right? So a long period of time, which isn't to say that Rohit and I are old. It just indicates that the breadth of work that was done here is truly expansive. And also, I think what's important to note here is, right, that Rohit takes a very unique approach that combines cognitive science and artificial intelligence, right, to understand human decision making and use that in a very interesting way to inform architectural design. It's a truly multidisciplinary work. Okay, so with that said, let's see any quick questions from the group. Yeah, and while people either sort of digest or they formulate the questions, so a quick question for you. Right? So you studied these various factors. Signage, space, memory, right? And you've mostly studied them in isolation, right? Yeah. So how would you go about even beginning to model these in sort of the combinatorial complexity of these things in tandem, in unison?
Yeah, so one way is to conduct more experiment by having the combination of this. Like we have an experiment with signage with the space and signage with the memory, or the other one is which takes a more mathematical approach, which is to go in the direction of multivariate decision making. So you have different variables, and you try to compute the uncertainty within those variables and then uncertainty among those variables, and then you come up with some kind of a probability function which can give you one result. So we in one of our paper, we slightly touched upon it, but I have to dig further in that direction to figure out what will be the right way.
Okay, wonderful.
So
Okay.
there's one method called like Dempster-Shaffer theory, which is what we use. So yeah.
Yep, sounds great. Okay. All right, great. So it looks like there are no questions, right? So in that case, why don't we virtually thank our speaker, Rohit? Yeah, thank you for that wonderful talk.
Thank you.
Okay, so Rohit, I know it must be extremely late for you. So yeah, I think you're of course free to stick around if you wish, but please feel free to drop off the call. So we'll mostly be talking about class logistics and other assignments and all of that. So not that interesting for you probably.
Sure. So I will drop from the call. And again, thank you so much for this opportunity. And I hope someone will reach out. Please feel free to reach out if you have any questions, either on the particular slides, what I presented, or about the work which I am interested in doing in future. So thank you, guys. And I will head out. And thank you, Mugusir.
Thank you. All right. Okay. So what I propose we Uber on, right? I was going to ask if should we take a few minutes break, but I suggest because what I've come to realize is that these Zoom calls actually tend to be even more exhausting than in-person classes, right? So why don't we keep going, and we can try to end early. So so I think what we'll do is we'll go over the last week's assignment, right? Where you all hopefully have done a literature review based on your projects. But before we do that, are there any general questions from the class? Any questions, any topics that you all would like me to touch today? Any comments? So so I believe you all have now had 3 guest lectures, right? So Sam, Honglu, and now Rohit, right? And all 3 of them were sort of extremely diverse, right, in their topics, right, in their topic selection. So how have the guest lectures been so far? Can I get some reinforcement, positive or negative? Okay, no comments, right? Okay, so so if people have an opinion, right, but are maybe cautious not to share it in a public setting, please feel free to DM me later. I'm also thinking of perhaps even setting up an anonymized survey, right, to collect feedback on these lectures. But yeah, maybe at a higher level, right? I think hopefully the point of these guest lectures, right, is for you all to be introduced broadly, right, to an extremely broad selection of topics, and I believe that is being served. Second, especially with the last 2 weeks discussions, right, where Sam and Honglu should have both provided feedback on your various projects, right? I think that is an opportunity for you all to collect unique perspective, right? So I think I can certainly go on keeping on giving you all feedback, but that is only a single person's point of view, right? So I think it's equally important for you all to collect opinions and feedback from different sets of experts, and of course use that feedback, right, to further your own individual projects, right? So hopefully that is also happening. If you all have suggestions or guidance, right, on how you all would like us to adjust that feedback, please do let me know, and I'm certainly happy to keep that in mind. Okay, so with that said, why don't I share my screen? Okay, so hopefully you all can see my screen. Right, so can you all see like an Explorer window with your assignment submissions? All right, sorry, I'm just trying to figure out my setup. Give me a second. Okay. Okay. Yeah, so what I'll do is I'll proceed to open each of your submissions one by one, right? And I'll ask the groups to sort of come forward and to briefly present their literature review. Okay, so I don't expect you all to describe your whole project again, right? But just provide a very brief update on maybe what were the most relevant papers or topics that you all read, right? And how that was relevant to what you all are doing. Okay. And this will also be a way that I essentially, I mean, I took a snapshot of who was present, but I'll also be taking attendance. Okay, so let me. Okay, so the first one is counter training object detection. Right, so can that group please unmute themselves, right, and briefly present their literature review.
Hi, Professor. And hi, Max, Edvis. Are you guys there?
Yep.
Okay. Actually, I prepared a brief version of literature review slides for this presentation. Why don't we, so I can share my screen to present that, if that.
Yeah, please go ahead.
Okay. 1 second.
Yeah, and while they set it up, I just wanted to make a quick comment on P1, right? I was incredibly impressed with the quality of the project proposal submissions from the group, from the class in general. Yes, keep up the good work. Yeah, are you having troubles sharing your screen?
Yes, it says I cannot share the screen while other participants are sharing. So
yeah, okay, sorry.
Just simply take it
yeah,
over.
do you want me to stop sharing?
Yes, I think it required that.
Yeah, just give me 1 second. Yeah, stop sharing. Okay, done. Go ahead.
Okay, can you guys see my screen?
Yes.
Yeah, that's good.
Okay. So I want to give a brief overview of the model that we are proposing. On the left-hand side, that's the YOLO model. So when we say counter training, it's more common in the academia using the term as the arrow-driven learning. And here's a whole picture of the model. We want to create a arrow-driven learning way for a specific task. In this case, we use object detections, and we choose YOLO as the model. And YOLO is basically can be retrained by COCO dataset, which is a very common dataset. And we are going to use a vehicle dataset to do a transfer learning of the YOLO model. And then YOLO will make the predictions, and the predictions can put to another side of the model. On the other side, it's basically used to automatically generate the arrow annotations, which means here's example. If here I don't think you guys can see this picture. So the picture here is a false prediction of YOLO. It predicts a Paul as a person, and we want some kind of supervision can automatically figure that out and tell the model. And here we did a throughout literature review, and we come up with we think the prototype network will be a good solution. It relies on the backbone of ResNet, for example, and ResNet is trained by ImageNet, and we can use the vehicle dataset to fine-tune the prototype network, and this can be used to recognize any unseen class. For example, Paul is unseen in the objects of interest, then we hope this prototype network could tell YOLO that that is a false prediction, and we are going to use a first prediction to do the arrow-driven learning and further improve the performance of YOLO. And this way could be a online learning, could be made online learning, because we can use a streaming video to keep this process going and keep fine-tuning this two model. And that's the whole that's the overview of that. Any question? Did I go too fast? I'm gonna talk about the literature review related to this after that.
No, that's great. Please keep going.
Okay. Then let me check. Okay, so in terms of the thing I talk about, there are a few terms in the academia related to our related to the thing we're doing. And one is the error-driven learning. There's a paper published last year, which is learning from mistakes. What it did is adequately weight the penalized coefficients for each class according to their validation laws. And I think we can definitely borrow their idea. That is what we're gonna do in the error-driven learning for YOLO. And they did this for classification, but I think their model can be easily extended to an object detector.
Yeah. So adding on to that, so like the learning from mistakes paper, I also read, and I didn't add this into the slide, but it's in the document that we submitted, Professor. So learning by passing tests is another similar paper. And basically, it aims to look into whether models can be trained by administering them tests, right? So it's sort of like a you have your normal model, and then you have your learning by passing tests model, which is sort of like a teacher and administers tests, and it creates more difficult tests as you go on. So that's sort of like an iterative process that is sort of similar to what we might be trying to do here. It's the last one. Yeah.
Okay, sounds great. Thank you. Anything else to add, team?
Yes, as a second term, I learned from the literature review is the zero-shot learning. It's more referred to recognizing unseen class for this. So this is what we're gonna use in the prototype network. We expect this can recognize unseen objects. And in this build, we found the prototype network and its variance is useful. It basically based on a pre-trained model, for example, ResNet trained by ImageNet, and then they compare the feature of new samples with existing clusters in the feature space, and this could be also augmented by unlabeled data. So and the other way approach in zero-shot learning could be meta learning. It uses prior knowledge in lower levels, such as attribute and keywords and some knowledge graph for the regressions. And by doing this, they don't need any samples from the new class, just a metadata vector from of that class, and they can predict if that is a unseen class.
Can
okay.
I just to add on a little bit, I also read a paper on meta. It's towards the top. I don't have to go into all of it, but just about training an object classifier using few shot learning, and which is related to zero shot learning and meta transfer learning. So hopefully that can also inform that part. But that's all I wanted to add.
Okay, thank you, Max.
Mhm.
And the last thing I think is related is the fine grenade classification. Since we both the YOLO model and the prototype network has been through a transfer learning, I suppose any mistake the YOLO make will be fine grenade, like just two similar class. One is in our interest, one is not, and we are more like we expect the mistake will be more frequently from that scenario. And in this case, we are going to use some techniques from the fine grenade learning, fine grenade classification to better fulfill our goal. One is the multi-attention, multi-class constraining, which is published in 2018. It learned the multiple attention regions feature of each input images, so they can just pull the same attention, belong to the same class feature closer, and then push different attention, different class objects away. And the other one is object central mechanism. They just automatically use a model to focus the image on the key features. And then it's the deep ranking. That this one is a more pure computer vision related one, which use a combination of handcraft features to create a training set. The training set is a triplets, which contains a core grenade images, a normal one, and a 5 grenade images. They train this in a contrasted way, and then to predict the ranking of the grenade. And I think that's all I read from the literature review. Guys, Max, you have any comments to make or add?
I think I'm good as well. I also read the YOLO V4 paper, which is what we were going to do transfer learning on, and their whole the way they did their ablation study and their experiments was very interesting. So maybe we can use those methodologies in our paper. But yeah, basically that's it.
Yeah,
Okay,
I mean, I also read papers, but on similar topics to these other ones.
Okay.
Okay, excellent. Great job, team. Yeah, just to reinforce Advit's comment, right? I think I strongly encourage you all to reuse and repurpose, right, experiment protocols and ablations from other papers. Don't try to reinvent your own, right? Because the more you stay close to existing evaluations, it gives more grounding to your own. Okay, wonderful.
Thank you, Professor.
Yeah, I think yeah, because I know we're a bit short of time today, so I'll if there is a question from others, yeah, just feel free to jump in. Otherwise, I'll keep going. Okay. So next group, the door differentiation project. So I won't share my screen in case you all want to share your own. So is that team present?
Yeah, I can share our literature review. Give me 1 second.
And yeah, and y'all can be brief, right? So y'all don't have to be very in depth, right? Just broad strokes, right?
Yeah.
Go ahead.
So we sort of are thinking of our project as sort of this two-step process. So door differentiation is sort of the first part, being able to, see a door, like we know that there's a door there. And so being able to classify what kind of door that is. And then the second part of it is sort of object detection, looking at, well, are there signs? Are there door handles? Are there clutter in front of the door? And so that's sort of how we've divided up our project. And it's also sort of an approach to our literature review. So in terms of door differentiation, we actually haven't been able to find any literature specifically dealing with door differentiation. So what we actually read was a lot of papers on door detection, which gives us a good starting point. And there actually is a lot of literature on door detection using different kinds of models. So obviously there's the paper that we originally used to sort of base our project proposal on. They have an extended study which actually did identify exit or handicap signs. And what was sort of novel about their detection model at the time was that it could identify a door based on only 2 edges being visible. So if a door was partially occluded, it could still identify the door. We also read a couple other studies that sort of looked at door detection in sort of narrower environments. So one of the papers that we read was specific to automatic doors at convenience stores, which was interesting because a lot of models have difficulty being able to differentiate between glass doors and windows. So that's something that's really helpful for us, but obviously like door differentiation is not the focus of these papers. And so what these papers actually offer us is more of a starting point rather than something that we can use as sort of the core of our project. And then the second part was object detection. There's obviously like a lot of literature on object detection. We picked a couple of studies that focus on object detection to aid visually impaired people. And so one of the things that we found interesting here was obviously like studies that look at deblurring. So if you were to use video input, you might not have sort of clear images every time. There were a couple of studies that we're doing door detection and that we're also able to identify clutter. So studies like that were really helpful for us as well. And yeah, I don't know if anyone else from the group wants to jump in as well.
Yeah, so I guess the reason we focused a lot on object detection papers, I'll just add on, is that essentially both of our kind of phases for the project are just specialized object detection problems. So yeah, looking at these papers, although they're not going to be necessarily like working exactly the same way as our model, we can take a lot of the different aspects they've used and a lot of the different approaches they describe and apply them to door differentiation as well. And then also for the papers that there were a few papers we looked at that are just like full scale, like deployment of some of these models to aid like the visually impaired. So those are a good way to look at, those are good papers to look at if we actually are able to get to the deployment phase. One of them included a fully kind of modular approach that would that had like, you know, taking camera input, passing it through these object detection models, and then outputting it as like audio input through a speaker using a Raspberry Pi to you know, the visually impaired user. And that would be easy to apply to our project because essentially all we'd have to just recreate the results of that and then just replace their object detection model with our own door differentiation and detection models.
Okay, excellent. Yeah, so I'm actually reading and writing down my feedback, right? So y'all can watch out for that directly on Canvas. All right, wonderful. Thanks, guys. Thanks, team. Great job. Let's move on to the embodied conversational agents team. So I know there are three of you all, right, doing your own things, but all three of you all can present together. So starting with Surya. Is Surya there? Okay, Abdullah. Nope.
Hi.
Are you there? Yeah, go ahead.
I'm pulling it up right now. Okay, you can see it, right?
Yeah, good.
All right, so yeah, I'm working on the embodied conversational agent project with Jerry. You know, a very brief overview of what the project is intended to do. We're creating a conversational virtual agent, kind of something I can speak to, and then from the input text, it will formulate its own response. So my specific role is the gesture synthesis, so incorporating the upper body hand gestures and audio on this. So I was looking at papers, of course, related to that. This was the main one I've been working with, visual effect gestures, working on reproducing that. So earlier today, I was able to get it running and everything. I'm going to start off by modifying this one. What they did is right here. So they input. So they worked with very large data sets of human video. So people speaking, and then they would extract the raw speech, so the audio. They had a real straightforward section, speak ID, and had the from those they would decode them, kind of understand exactly or encode what exactly, how I can quantify each one of these characteristics, and then from there we were able to create this this artificial intelligence that given each it can recreate it can create hand gestures. That was their work, and then I'm going to start by modifying that a little bit and playing with the inputs for now. Another one I worked with was also another part of my work is the surveying the validity of it. So how accurate do these given emotions represent? Do these given gestures represent given emotion? So they had a lot of work with that. So I was looking into that. And then another one, Anika Vera has a lot of work when it comes to emotion perception. So kind of what exactly does it take to simulate an emotion? We're kind of quantifying that. But my approach to this is rather going to be similar to this one, where they surveyed assess his accuracy, but his work was very interesting. I think that's all.
Anything else?
No, that's all.
Okay. Does just giving? Do any of the other team members want to speak up?
Yeah, Professor. So
Yeah.
my presentation is actually a little different. I'll share that.
Yes, please go ahead.
Yeah.
Yeah, and again, very brief overview of most relevant prior work. Don't have to re-describe your project.
Yeah. You can let me know when it's visible.
Go ahead.
Yeah, so in my literature review, I kind of approach the field of 3D facial reconstruction and rendering from how it started off. So I just initially talked about some of the pioneering work in parametric model for human faces and how that kind of paved the way for all the other models and how they were created. Then I moved on to techniques that kind of optimize by an analysis by synthesis fashion and use them to create some sort of facial reconstruction by some statistical models. So these three papers are pretty much related on that by using some sort of CNN or deep neural networks to try to recreate faces. But the issue with that is the overly smooth reconstruction. So the faces look kind of unnatural. The next set of work is where they trying to use like high frequency geometric details. So some sort of coarse facial geometry texture. So the problem with this again is that they try to bake in the details after the construction. So they try to bring in more detail, but the problem is that it looks like it loses the realism because it looks like it's artificially like more like a game. Like if you see some of the older games, like how the faces look, it looks similar to that. Then I kind of analyzed on other techniques that use some sort of mesh or voxel reconstruction method to better do the process. And the last three papers are pretty much the state-of-the-art work that I discussed in the last class. So these kind of, especially this last paper called DECA, so it splits both reconstruction into two parts where they think of it as one part, which is the coarse reconstruction, which is most of the features in a face, which are pretty common among people, and the fine details, which are parts which are like facial wrinkles and other parts that are detailed and might even change depending on the expression that a certain person does. And then adding that displacement map onto the 3D reconstructed face. So yeah.
Excellent. Yeah, thank you, Rajat. Thank you, Abdullah. All right, let's keep going. Yeah, sorry guys, I'm speeding through this, okay? So GeoPixels?
Yeah, I'm here.
Yeah, please go ahead.
I don't have anything to share my screen, so if you could please share your screen, I appreciate.
Yeah, I'm doing it. Please go ahead. Please begin describing your problem. Yeah, so hopefully y'all can see, right?
Yeah, as you know, my project was to find the locations, georeferencing the pixels of a natural image. There are several methods in the literature. Some of them used matching some key points of the images with DEM. My literature review focused on the studies that use a single image and DEM. In these studies, maybe one or two camera information was known, were known as prior information. For example, in one study, they assumed that the longitude and latitude of the camera were known, and in other studies, field of view was assumed to be known. But in my case, all of them are unknown. There is more challenge in my study. So one of the techniques that they used in the literature was to use skyline, detecting skyline and match the skyline with the reconstructed scene from the DM, and then matching those lines with the those skylines in the DM and the image. And the other method was to use key points from the images and matching with the local maximum height points in the DEM, which is not very efficient in all cases. And the most recent case, and which is most efficient in the literature, is to overlay a real imagery or real satellite imagery on the DEM, and then comparing the features of that textured DM with the image. But the textured DM features are considerably different from the features of the image. So they used a data driven method to learn the features and compare them. Yeah, that was the most recent paper.
Okay, thank you. All right. All right. Sorry, I was screen. Heather, thank you very much. Okay, let's keep going. Graph sketch query. Oh, looks like. Okay, so we'll move on to the next one. So yeah, imitation. Which team is this? I don't know. Yeah, the imitation learning team. Are you there? Okay.
Okay. Can you hear me?
Yes. Okay.
Okay, sure, thank you. So for this project, we mainly discuss imitation learning with spatial temporal data. So for I like to share the later review in the first part, let's say the imitation learning with spatial temporal data, and then Zejun will share something, let's say optimal transportation in imitation learning. So for the first part, we like to somehow like transfer learning, which that learns the experienced agent's decision-making preference in some popular regions, and utilize this knowledge across agents and cross locations. So for state-of-art imitation learning methods with spatial temporal data, they mainly use GAIL, which is generative adversarial imitation learning. Well, we like to use a different method, which is optician transportation, which is widely used in computer version and robotics. So that's the first part, and then Zejun will share this.
Okay, can you hear me?
Yes.
Okay. Yes. Now I will briefly talk something about cross-domain imitation learning. At first, the imitation learning, a very early approach is behavior colonial, and after that is a key process is inverse reinforcement learning, and in the 2016, some researcher in Stanford University proposed method means GAIL, GAIL. GAIL shows the IR is the theory of a parameter matching problem, and propose advisor object whose optimized optimize the behavior. And recently there are some work about use optimal transport, such as PWL and SIL. They use optimal transport to do the imitation learning, and it shows has very good performance in some tasks in vision and robotics, and also they use the optimal transport can do some transfer learning things, which is cross domain. So we want to try use optimal transport method to do some task in spatial temporal data. This is my our thought. Okay.
Okay, all right. Anything else? Okay, thank you very much.
Okay.
Okay, let's go on to the next. So impact prediction, I believe, is not here. Music-driven animation.
Hi, can you hear me?
Yes.
Okay, so I researched on 3 papers, and I mean, I researched on a lot of papers, but these 3 papers I found were the most relevant. So in the first paper, they basically used different joints, and they processed the keyframes animation, and from that they created the animation of walk cycle. So they created a lot of animations, but they put the example of walk cycle, and everything was nice about this paper, but there was no music signal or motion mapping to the music signal. But we can use this paper to generate motion signal, and we can use this for generating animation from the modified motion signal as well. In the second paper, it's basically motion signal processing, and this is a really nice paper. There were a lot of citations of this paper in the other papers that we researched on. So in this paper,
yeah, please keep going.
Yeah, so in the motion signal processing paper, they used the first paper to generate to get the joints and the data, and then so for example, if we consider knee joint, then in a walk cycle, the way the knee joint moves, they created a signal from it. And in this paper, they also tried to blend 2 motion signals. So like there is a drunk walk cycle and military march. So they tried to blend the 2 motions and they created new motion. And they also had an interface uh, to change the degree to which the 2 motions are blended. So if you try to change the degree, then sometimes the walk becomes too cartoonistic and too unnatural. But if you set the degree correctly, then the walk is the new modified walk is actually pretty natural. So we can use this to understand how the 2 signals are mapped. They also consider time warping algorithm. So the 2 motions are blended in such a way that the time matches. So it doesn't happen that the first part of first motion signal is mapped to second part of the second motion signal. So they are coordinated well. In the third paper, so it is for the music part. So in this paper, they use MIDI signal with audio signal, and they pass it with a low pass filter, and they get beats from it. And in this paper, they directly use a motion signal. They haven't discussed how they created the motion signal in depth. They just referred some other paper, and they and then the beats were mapped with the motion signal, and they modified the motion signal. So it's not like they created the motion signal from scratch. The new signal that we get is actually just edited, and it is not created from scratch. So it is more natural, and there is no jitter or anything. So it is either stretched or shrunken. So Gunjan, can you please take over?
Yeah. So in the fourth paper, they focus mainly on developing high quality motions for a humanoid robot, which was mostly intended for a robot theater. So they took the sound file as an input, and the output was the set of the movements which were for the robot. So for the music thing, they encoded the music in MIDI format, and then the music pieces were like laid out in a plain text, and then the relevant information were extracted using that plain text. And from those information, then they mapped the motion data for the robot by using a set of their own production rules. In the fifth paper, they proposed a music-driven piano performance generation using 3D motion capture data and recurrent neural networks. So they basically focused on how to visualize a robot playing a piano performance, and they used neural networks, which is the LSTM network they used. And for extracting the beat information from the music, they used Mel frequency cepstral coefficients. And for them, it proved to be quite good, and it gave out good results for the beat information from the music. And they also had their own production rules. So they mapped the beats to the movement of the 3D motion animation. In the sixth paper, they divided their project into 3 parts. That is the music analysis, the motion analysis, and the integration of the music and the motion, so that they can project it in a virtual environment. So for the music analysis, they use the low pass filter to the audio data, and they also use some other algorithms to overcome the problem of connecting the waves, connecting the gaps between the beats. So they use low pass filter and some algorithms to extract the relevant data from the music. And they constructed motion graphs which will map with the beats information. So yeah, that was the main motto of that paper. So yeah, all the remaining papers also focused on collecting the main data from the music and then mapping it with either it can be animation or mostly it was for a robotic movement.
Okay, sounds good. Thank you so much. All right, let's keep going. So one short story synthesis. Are you there?
Yeah. Hello.
Yeah, go ahead.
Yeah. So basically, in our literature review, we reviewed a bunch of papers. So basically, for our approach, we need to generate some set of captions from our input image, and then use that caption to basically generate a story which will be foundation for subsequent images to be formed. So for that, we need to have an accurate enough image description of. So for that, we thought of using just the clip model, but that's an encoder decoder model which does not accurately describe the image and it's not able to generalize well. So we used a paper by Salesforce named Blip, which is able to do this because of a new model architecture they presented. So for generating our captions, we'll be using that, and it has been showing pretty good accuracy. And to use that caption to generate story, we are using a 2018 paper by DeepMind called Hierarchical Neural Story Generation. So basically, they use a fusion model to generate the story, and it has its limitations, like it cannot work with very large scale stories, but it works perfectly in our use case because we just need short stories as a foundation for our subsequent images. And for our approach, we thought of 2 approaches. Basically, there's one where we can fine tune our model on a specific sketch-based data set and use back propagation on the differentiable on a differentiable vector-based rasterizer. But that approach will force us to use a specific data set, and that may hamper our work's generalization capabilities. So we are going to a evolutionary based approach like used by Clipasso and ClipDraw, and they had so basically what they did was they used a clip-based perceptual loss to basically generate the images according to the input text, and it has been working pretty good, but it just takes a lot longer time than normal methods rather than evolutionary methods. So yeah, we're thinking on improving this by using visual VAEs, but we're still experimenting in that area.
Okay, very good. Have you all been able to like reproduce any of the basically assuming these models? Okay,
yeah.
So you're already playing around with these models, right?
Yeah. So we have been able to reproduce like blips results, and we've also been playing around with Clipasso's model. They just like released the code like a week ago for Clipasso. So we've been able to generate some stuff right now, and the hierarchical neural story generation is also working properly.
Okay,
so,
excellent.
Yeah.
All right, thank you very much. Let's keep going. So next is pyramid guarantee.
Oh, it's my turn, Professor. I can share my screen.
Okay, so let me stop sharing. Yeah, take over.
Okay. Thank you, Professor. Hi, I'm Richard, and I'm still working on the perfect image generation. And today's literature review will, from the aspect of three parts. First is the framework innovation, and second part is the NAC innovation, and the third part is the innovation of the attention pyramid. First, let's begin with the framework innovation. And before the GAN alphabet, they use VAE techniques like VAE are they used to generate images. But when we find the GAN more powerful tools, most of the people switch to this technique to generate the images. The first paper to use GAN to generate person images it's a pulse guided GAN, I think it's named. And they use the technique they use is based on the conditional DC GAN, which means they use some convolutional layers that with a small reception field, which is limitation of the CN. And to solve the problem, the FOTA networks, the backgraph GAN and the thin GAN, I think it's pronounced, they use the more powerful frameworks to capture the crossing long range relationships. Why do they use that? Since because they want to capture the relationship between the input pulse and the output pulse, so that it can generate images with better qualities. And the second part is the innovation on the NAC. What is NAC on the deep deep learning. It means the part that invert between the backbone and the output. It is widely used to fuse the features that extract by the skeleton and to enhance the feature for the output. So here are some innovations on the neck. The first one is widely used in object detection. It is the feature pyramid networks, which use a feature pyramid. I think the first one to use the feature pyramid in the object detection task. And prior works, things like Coordinate or the other things like that are based on the non-local blocks. Since they also want to capture the long-range relationships. And in the person REID field, they use the APNet, which means the attention pyramid, to combine the attention mechanism and the pyramid, feature pyramid in the person REID field. Also, since our work is also based on the attention mechanism and attention and the feature pyramid, the third part of the literature review is based on focus on the attention mechanism and feature pyramid. Regarding to the attention mechanism, multi-head attention and self-attention networks are widely used. They are the most popular tools of the attention mechanism. And when it comes to the feature pyramid, there are still a lot of works based on the feature pyramid networks. And the first one is the path aggregation networks, which add additional bottom-up paths to enhance the entire feature hierarchy. And also there is adaptive spatial feature fusion. There are also works that based on the feature pyramid that add some path L to further fuse the features. And as we can see, the innovations go from coarse to fine, which is also the path that I follows. First, I select the framework as the baseline and make some improvement on the neck part to solve the drawback of the net part. I also find some ideas such as adaptive mechanism to solve the feedback. So, and currently I'm on the first step to reproduce the results of the my frameworks. It is to reproduce the results of background. However, since the model they given isn't optimized, I mean the hyperparameters they offer is not optimized. So currently I have some difficulties on reproducing them. Hopefully I hope I can solve them in the near future. Thank you. That's all.
Okay, thank you very much. And it's good to hear that you've already begun reproducing results. Okay, let's go to speech. Yeah, thank you. Let's go to speech to image.
Hello, Professor. Can I share my screen?
Yes, please.
Can you guys see my screen now? Hello.
Yes.
Okay. So basically, our project is to convert speech to a facial animation. And for that, we went through the different papers of GANs. So for that, we researched about GANs to generate the facial images and the animation from that. And for that, we went through different GANs, style GANs, and style GAN 2, PG GAN, DC GAN. And so we decided to go with the style GAN 2 because it seemed most ideal for our approach. And for generating audio to landmarks, we also researched on the various papers which were various research that were done, like image to image translation. And we also look at the audio driven emotional video projects which are focused on the emotional part of the emotional decoding the emotional part from the audio. And we went through the different papers which worked on the LSTM networks and different CNN and GNN networks. And we decided to go with the GRUs in generating that. And there was also animating face using disangled audio representation. That paper was really helpful to us because it was working on the similar kind of thing. And from all of these papers, we decided to compile the best of all these papers and to generate our uh, own model which can perform well in transferring audio files to video animation of facial expressions. And that is how we do it.
Okay, thank you very much.
Thank you.
Okay, so if I understood you, you said you're using StyleGAN, the V2 as your backbone. Is that right?
Yeah.
Okay. All right. And then, but you will have to extend that model, right, to consider to be able to take speech as input.
Yeah.
Okay.
Yeah.
All right. Yeah, we look forward to understanding how that will be. But yeah, good. Thank you. All right, let's go to virtual try-on.
Hi, Professor. Can you hear me?
Yes.
So let me just share my screen. Yeah. So we went through a bunch of papers and we tried to include the most relevant ones. So throughout all the papers, we got to know that there are mainly two approaches, that is 3D based and 2D based. 3D based obviously relies on 3D measurement data, so we considered only going with 2D based approaches. So yeah, so we got to know a bunch of concepts that are pretty common in most of the topics, and yeah, we started to research on a bunch of them. So yeah, so virtual image-based virtual try-on is again a 2D based network. Is also one of the papers we went through, and mainly uses pose data, pose heat map in order to segment the body key points such as arms, torso, etc. Again, this paper and our third paper, that is character preserving image virtual try-on network, are kind of similar. They mainly focus on preserving the texture of the cloth. And yeah, but the main problem they face are when there is an improper preserved shape information of old clothes, or if there is a rare pose or something of that sort. And the second paper we went through was VTOM HD, which is a high resolution virtual try-on via misalignment error normalization. So in this is the paper that we thought we'll go ahead with and try to implement this. So in this project, mostly they have talked about something called as alias generator, which is alignment error segment normalization. Throughout our survey, we got to know that the main problem, basically the main problem every model suffers through is the final misalignment thing. So here they have proposed something called alignment error segment normalization, which tries to correct the misaligned parts. So yeah, so we are trying to implement that one. So another paper we went through was something called ACGPN, which is adaptive content generating and preserving network. So ACGPN then during the pre-processing part, it tries to segment the body key parts just based on the segmentation map, not using force key points. Because of this, it suffers in pre-processing step itself. So it fails to segment the the torso and the arm part bit badly. So that's where it kind of suffers. So yeah, Andrew, do you want to talk on further papers?
Yeah, thank you. So yeah, so mostly these four were the essential papers that our project involves. So the other papers also we try to go through and check what's inside. So one was MG-Viton. So that is based on the multi-pose guided virtual trial network. So it uses a GAN, so it uses something called a deep warping generative adversary network, which warps the desired cloth appearance into the synthesized human passing map. And then basically its main advantage is it resolves the misalignment problem, but there is still a disadvantage where we do not get the photorealistic images, like realistic images. So it's somewhere like I mean the virtual Viton HD model, that was the second model, which it is much superior to this one. So we kind of use that one. The other are VT NFP, which is basically aims to preserve body and clothing feature, and it is again has some kind of limitations where we see some distortion and misalignments in the actual clothes, like where there's a logo or some pattern. So we see some sort of misalignments there. And then we also looked into cloth flow. Cloth flow is another model, another paper research, which is basically it basically works on semantic layout for getting a richer image, and it basically also has some disadvantages where we can see that some sort of distortion in the face or the body parts. So the other few were Fashion++ and TaylorNet. TaylorNet is basically a 3D based model, so that was not our main idea behind the development project that we are building. So we kind of got a high overview of that particular research paper. And yeah, so like there are like many more papers, but we essentially took like the Viton HD, ACGPN, and CP Viton for our project, which fits into our development part. So I think that's all.
Okay, thank you very much. So you said that you all have identified, is it a paper which you all will begin by implementing? Was that right?
Yeah, we thought we'll go ahead with the second one that we have here. It's virtual try-on with misalignment and normalization. So that's what we thought we'll go ahead, because there are a bunch of stuff which is common in all the other papers, and we observed that in this paper it has got almost everything sorted out. So we thought we'll go ahead with that.
Okay, sounds good. And will you all be implementing this from scratch, or is there some startup, like some open source software available?
Yeah, I mean, we have a pre-trained model is already available for us on this particular paper. So we thought we'll use that and we'll code it up from that one.
Okay, wonderful. Yeah, highly encouraged. Okay,
Yeah.
sounds good. Thank you. All right, last, I think that's the last team. VR space design. VR space design, are you here, Karthik?
Oh, hi, Professor.
Yeah, go ahead.
Let me share. Can you share, Professor? My computer is not letting me.
Okay, give me a minute.
Yep. So just quickly, my project is going to be on using VR in order to better design public spaces post-COVID.
Having, yeah, share screen.
So for my research,
Okay, hopefully it is.
yeah, it's showing. So for my literature review, I looked at 3 types of articles. The first is anything to do with VR and urban environments and how this can be studied, but also like psychological questions, because my mentor is a psychology PhD, so she wants me to look at like from that perspective as well. And then also how to, I guess, involve COVID-19 and see what kind of research they're doing into that in public spaces. So in terms of papers, a lot of what I found was in terms of digital twins. A lot of it was focused on creating 3D models, mapping, and how to involve, I guess, citizens in this approach to urban planning. Most of this was limited by the technology present. It appears that realism is the biggest handicap in terms of getting good results. That's what most of the authors reported. They found that people, because of the different, or if they could tell the difference between real life and virtual, they were not providing good results in terms of how they interacted with the environments. So since my research or my project is going to focus heavily on how people interact in public spaces based on COVID, I tried to look for ways, I guess, to get people to respond. So some of these literature papers involve people. That first one involved, or one of them involved a digital twin in Herrenberg, Germany, and they tried to involve people with they showed different parts of the city and traffic volume and pollution and different models, and they tried to, I guess, get people to respond in 3 ways. They liked it, they didn't like it, or they were neutral. So I guess that would be one way to query results. Other papers gave respondents 3 different choices and then had them either pick one of the choices or not. Others did logging, which is, I guess, straightforward in terms, especially for VR, like where they're walking and how they're interacting with the environment. Other approaches involved using more, I guess, more simulations. So one of them involved a COVID-19 mass vaccination center, and it studied how these centers could be better designed in order to move patients through. So this was more of a simulation because it didn't really involve people and their interactions. Another paper was about manufacturing systems and creating digital twins to look at how to do this. Again, it used VR in order to build the facilities so that everything could be done more efficiently. So I guess my project is going to focus heavily on where to place objects within the environment. So that is important, I guess, because how the objects are placed can determine whether people find a public space, a place they would feel safe in post-pandemic. I also looked at some psychology papers to see how people interacted with different types of spaces. So I found that a lot of research focused on green spaces and blue-green spaces, and found that these are more conducive, so they might be more positive. So that focused me, I guess, on building a urban space that's like a town park of some sort. So I'm focused on creating that and then testing it with my mentor. Uh, Apart from that, a lot of the focus was on creating, again, a digital twin that replicates a part of a city and then see how people, I guess, interact with it in order to improve urban planning. So I want to take that as also a focus. But in terms of limitations, the biggest looks to be realism, because that does create differences in how people respond, and also the type of questions asked. So I found from the authors, the simpler questions are better in terms of I liked it, I don't like it, or neutral. So I guess, yeah, that's what I found.
Okay, wonderful. Thank you. Yeah, and I spoke with Serena. Yeah, I definitely encourage you to also be involved not only in the of course the design of the environment and everything, but and also the Unity part, but also the experiment, right? So definitely involve yourself in that, so you can play a role in designing the experiments. Okay.
Okay.
Good. Excellent. Thank you so much. So I believe that brings us to the end. Is there any team that we've missed out? Okay, so I think that, yeah, I believe we've done. So before we conclude, let me just, yeah, so let me, sorry, just go ahead and share my screen one. Oh, I believe I'm already, but let me switch one second. So let's stop sharing. Share screen one. Okay, so hopefully you all can see the Canvas website. Yes? Okay, so I'll take that as a yes. Yeah, we just want to quickly inform you, all right, about next week. So next week is easy, right? Not so it's basically mostly logistics, right? Setting up your repository, your project report, and weekly updates. So yeah, so please go ahead and make sure to do all these things. Essentially, right? It's not a lot of effort for next week, and especially set up your Discord channels. Okay. So if I can, let's see if I have Discord on. I do. Yeah. So basically here, right? I expect everyone to create their own channels, right? Project name or whatever, right? So please go ahead and create your channels. Let me know if you all need access. Like if you all are unable to do this, in which case I'll have to go into. I believe you all do, right? So you all should be able to create your own channels here. So please do that. Please attach your the links to your proposals and your literature reviews, right? So that we can all read up on your projects here. And I encourage everyone, right, to be aware of other projects, and feel free to interact, feel free to provide comments, ask questions about each other's projects. Okay, so I hope that this can turn into an engaging conversation moving forward. Okay, so yeah, I mean, essentially, right, that's what I've written here. So please do that. Any questions? Any questions before we end today's class? Yes. Do you have a question?
Professor, I don't think we can add the projects in the Discord channel.
Okay. Okay. So let me, offline, let me take a look if I can change the permissions, right? If I cannot, then I guess I will have to do it, right? So yeah, let me try and change the permissions. Otherwise, I'll go ahead and do it myself. Thanks, Catherine. Any other questions? Okay, so if there are no further questions, I think we can go ahead and end today's call. Yeah, so I think I'm trying to finalize the next week's speaker. So hopefully I'll send out the announcement in a day or two. All right, so watch out for that. Yeah, so I'll be on Discord. If anyone has any other questions, feel free to DM me. Otherwise, have a great week, and see you guys hopefully in person. I'm not sure about the status of our speaker. He or she may not be in the country, right? So I'll let you know. Okay, so I'll let you know what the logistics of next week's class will be. All right, have a good week, everyone. Bye.